So objective bits now. Which of the following molecules show optical activity? Okay. So here 4 different compounds are given, A, B, C, D. So this is biphenyl compound. Okay. So even though it does not contain any chiral carbon atom, but it exhibits the optical activity when it contains substituents at the ortho position. See here ortho position, bromine and iodine all are substituted. So it exhibits the optical activity. Okay. And this is example for allyne compound. So carbon either side, double bond. Okay. So this is also exhibit the optical activity. And see C and D. C and D contains chiral carbon in it. Okay. So that's why these two compounds are also shows the optical activity. So that's why A, B, C, D. So all these compounds, they exhibit the optical activity. Okay ma? Next. See this compound. pH. pH here phenyl group C6H5. CS double bond CH and one cycloalkane ring is there, followed by double bond Cl CH3. Okay. So this is the polyene compound which contains cyclic ring in it. Okay. Now you have to calculate geometrical and optical isomers. And first coming to geometrical isomers. This is the compound having different ends. Okay. If different ends are there, we use formula 2 to the power n to calculate the geometrical isomers. We use the formula 2 to the power n. So here n indicates number of double bonds. N indicates the number of double bonds. But in this compound, 2 double bonds are there and 1 cyclic ring. Here cyclic ring also considered as double bond. Okay. So that's why we take n value as 3. Okay. And according to this 2 to the power 3. So 2 into 2 into 2. So total how many geometrical isomers? 8 geometrical isomers. Okay. It forms 8 geometrical isomers. If a polyene compound consists any cyclic ring in it, so that is also considered as double bond. Okay. So number of double bonds in this compound, you can consider 3 but not 2. Why? Because cyclic ring is also considered as a double bond here. Okay. Then coming to optical isomers. So to exhibit optical isomerism, what is must? Chiral carbon. So overall in this compound, chiral carbon is there. For example, here this is the chiral carbon. Okay. This is the center where chiral carbon is present here. Okay. So one chiral carbon. So it is surrounded by 4 different groups. Okay. So 2 to the power 1. Okay. So 2 to the power n. This is asymmetric compound, unsymmetrical compound. No symmetry is present here. That's why for optical isomers also, to calculate the optical isomers also, we use this formula 2 to the power n. Okay. So here n equal to 1. So number of optical isomers 2. So 8 and 2. Okay. Next. The correct statement about the compounds A, B and C. Okay. So these are the compounds. So A, B, C. So here options A and B are same. A and B are diastereomers. A and C are enantiomers. A and B are enantiomers. Okay. A and B are same. This is not correct. Why? Because groups are, COH group is in A, COH group is at the bottom position and in B top position. Okay. And A and B are diastereomers. These are not diastereomers. Why? Because OH, H groups are superimposed with each other. Okay. Okay. So that's why these are not diastereomers. And they are not superimposable with each other, but they forms the mirror images. Okay. So that's why A and B are enantiomers, but not the diastereomers. Okay. So this is Fisher projection formula. Okay. You can write a COOH at upper side. If a mirror is there, okay, its image is like a B. A image is B. Okay. A reflects with its image as B. So that's why both are enantiomers. So A and B both are enantiomers. Okay. Next, see this compound Cl, and it contains 2 cycloalkane rings and also 1 double bond in it. Okay. So in this compound you have to calculate the number of stereoisomers. Okay. So number of stereoisomers. To calculate number of stereoisomers, here both the ends are same. Okay. And formula is 2 to the power n minus 1 plus 2 to the power n plus 1 by 2 minus 1. Okay. So formula 2 to the power n minus 1 plus 2 to the power n plus 1 by 2 minus 1. So this is the formula. Okay. So what is n here? N indicates number of double bonds. Here it contains 1 double bond and 2 cyclic rings. Okay. So just now I told cyclic ring is also double bond. Okay. So how many cyclic rings here? 2 cyclic rings. So total number of double bonds here is 3. So that's why n is 3 here. N is 3. Okay. So 2 to the power n minus 1. 2 to the power 3 minus 1. So 2 square. Okay. 2 square. Plus 2 to the power n plus 1 by 2. So here n is 3. 1 double bond and 2 cyclic rings. Okay. So n plus n, what is n? 3. 3 plus 1, 4. 4 by 2, 2. Okay. Minus 1, 2 minus 1, 1. Okay. So 2 to the power 1. So 2 square plus 2 to the power 1. So 2 square, 4. 4 plus 2. 4 plus 2. Total number of isomers are 6 isomers. So see this reaction, ma. So here this compound undergoes reaction in presence of hydrogen cyanide and we get 2 products, 1 and 2. Okay. So what are 1 and 2 here? Okay. So different options are there. Enantiomers, diastereomers, identical mesomers. See here 1 and 2 both are having same molecular formula, but these 2 are non-superimposable, non-mirror images. They are not superimposed with each other and they are not mirror images with each other. So that's why diastereomers. Okay. Next, coming to this. See the structures of 2 compounds A and B. What is the relation between A and B? Okay. So one having wedge formula. This is wedge formula, representation of formula with wedges, solid wedges. Okay. And this is dash formula. Both are same. Okay. That's why identical. Both are identical. Okay. Next. How many different stereoisomers are possible for this compound? Okay. So here 2 geometrical isomers are possible. Okay. If OH groups are present at the same side, that is cis isomer. Opposite side, one above and one below, trans isomer. Okay. So, two geometrical isomers. And it contains one chiral carbon. So, this is the chiral carbon. Surrounded by hydrogen, OH and different groups. Okay. So, that's why totally chiral carbon in asymmetric molecules 2 to the power n. So, n is 1. So, 2. 2 plus 2 geometrical isomers. So, total number is 4. Okay.